this module, we will be talking about, we will continue to be talking about approximation methods. I talked about variation methods, and furthermore, I will talk about variation methods later on. But in between, I will talk about another method which is called perturbation method. One of the approximation methods is perturbation method. And I said you earlier also that in quantum mechanics, we have only one equation, Schrodinger wave equation, and that we solve for getting the eigenvalue and eigenfunction of a system. And that's what we are doing since the beginning. There were some basic fundamental principles which we say postulates of quantum mechanics. So we learned first the postulates of quantum mechanics, and thereafter we applied those postulates and in order to solve the Schrodinger wave equation. And this Schrodinger wave equation, after solving, we got different eigenvalues and eigenfunctions for different systems. This is what we have done. And we started with a very simple system, particle in a one-dimensional box. And from there, what you got is the eigenvalue and the eigenfunction. The eigenvalue, if you remember, it was En square h square divided by 8ma square. And eigenfunction which we got is psi n is equal to root 2 by a sine n pi x upon a. Okay. So this was the first model which we talked about, and then we talked about, based on this, we talked about simple harmonic oscillator, rigid rotor, hydrogen atom. And then after I said you that if you go for higher order structures like helium atom or some molecules or something like that, then we cannot solve the Schrodinger wave equation, so we need approximation. And one of the approximation method was variation method, where in the previous module I talked about that we guess a trial function, and for the trial function we find the average energy from the expectation value postulates, and from that expectation value postulates, when you find the average energy, we can get the eigenfunction also and eigenvalue also. So this we have already done for different systems. Now the next method by which you can get the eigenvalue and eigenfunction for a system is perturbation method. Here the basic criteria is that you should have already in your hand a system for which the solution is available. That's called an unperturbed system. And there is a very small departure from this system, then only you can apply perturbation method. This is one of the, if you look at this picture, then it is this, the diagram of this cat will remain same except a small change on the cheek. When the owner of this cat is pulling its cheek, then a slight disturbance is taking place. So this is a perturbed system. The system is known to you, a small disturbance, that's called a small perturbation. Then only you can apply this particular method, perturbation method, and get the instead of getting the energy and eigenvalue and eigenfunction, you can correct the you can make the correction in the eigenvalue and the eigenfunction of the unperturbed system in order to get it for the perturbed system. This is what is the basic fundamental principles of perturbation method. Now, so perturbation method, for a perturbation method you need an unperturbed system. And an unperturbed system is system for which exact solution of Schrodinger equation is available. I said you particle in a 1D box, simple harmonic oscillator, rigid rotor, hydrogen atoms are examples of unperturbed system, because we have done the solution for these systems and we have got the exact solution for these systems. Okay, exact solution, I mean exact eigenvalue and exact eigenfunction. And a perturbed system is if you disturb this particular system, and perturbed system for which exact solution of Schrodinger equation is not possible. And when it will not be possible, when you slightly disturb the system. Let's compare with a cat. Particle in a 1D box with V not equal to 0 inside the box everywhere. What we have done in particle in a one-dimensional box, we have solved the particle in a one-dimensional box by taking an example like this one. X is equal to 0 to x is equal to L, and we say potential energy inside the box is 0. Now instead of this, if I say particle in a one-dimensional box which has same dimension, x is equal to 0 to x is equal to a, but now the potential energy is not 0. As you go up from x is equal to 0 to x is equal to a, potential energy goes on rising and it becomes equal to V x divided by a. Okay. So at a it will become equal to V, and and at x is equal to 0 it will be 0. Okay. So it's rising from this end to this end, or it could be slightly disturbed, like in one half of the box the potential energy has something else, and in another half potential energy is 0. So that could be a disturbance. Or in between the middle of the box you you add a potential barrier. Okay. So there could be many different ways by which you can disturb the system. So that disturbed system, that perturbed system, if you have to find out the eigenvalue and the eigenfunction, since one of the system, the base system, is known to you, so it's very easy to do through the perturbation method. And that's the application of perturbation method in quantum mechanics. Now you see, simple harmonic oscillator with potential energy V not equal to 1 by 2 kx square. Now this is known to you that in simple harmonic oscillator the potential energy is 1 by 2 kx square, and it's, if you remember, the psi naught for this is beta divided by pi raised to the power 1 by 4 exponential minus beta x square divided by 2. So this was known to you, and En we found as 1 by 2 V plus half h nu, where V is equal to 0, 1, 2, 3. Okay. So this is the eigenvalue, this is the eigenfunction for an unperturbed system. It's known to you. Now for a perturbed system, what I am saying? I am saying that you change the potential energy and add these two additional terms, and this will make the simple harmonic oscillator an unharmonic oscillator. And if unharmonic oscillators are very important when you will do the spectroscopy, you will learn the details about this one. So the only difference is that the potential energy of the simple harmonic oscillator is not 1 by 2 kx square, it has some additional terms also in an harmonic oscillator. So again, for this the base system is known to you, for the solution, exact solution is available, and what you have to determine is that how does these disturbances, these are the disturbances, these are the disturbance, these are the perturbation, these are the perturbation, these are the perturbation. So how these perturbations are influencing will influence the energy and the eigenfunction, eigenvalue and the eigenfunction for the system. Okay, that's the scope of perturbation method. Then hydrogen atom solution you have done, and we have found the solution for 1s orbital psi 1 0 0, okay, which was a constant value into exponential minus r divided by a naught, if you remember correctly. Very easy to remember by saying a constant, exponential minus r divided by a naught for 1s orbital. Okay. So this was known to you, but now what we do is that we place the hydrogen atom in an electric field and magnetic field, and the moment you place it in an electric field and magnetic field, the wave function will change and the energy will also change. And one of the earliest lesson which you have learned in your +2 standard or any physics book of the +2 standard or even chemistry book, you in the BSc, you have learned these two effects, a Stark effect and Zeeman effect. What do you say? You say that when you place the hydrogen atom in a magnetic field or electric field for a Stark effect or magnetic field for Zeeman effect, then there is a splitting of hydrogen atom spectral lines. And naturally, when the splitting of lines is taking place, it means the eigenvalue of the hydrogen atom does not remain same, it changes. Okay. So because of this electric and magnetic field, the energy levels will change and the eigenfunction will also change. So for this also, you have a base system, we have an unperturbed system, hydrogen atom. For this you have an unperturbed system, simple harmonic oscillator. For this you have an unperturbed system, particle in a one-dimensional box. Okay. So perturbation method has limitation that it involves with only those systems whose exact solution is known and there is a slight perturbation in the system, then you can account for then you can develop a method for finding out the eigenvalue and the eigenfunction for those systems. This is the limitations of the perturbation method, but even though it's very important, I will talk about later on. Broadly, these perturbation methods are classified into two categories. Okay, what we say is that there could be a time independent perturbation and there could be a time dependent perturbation. Time dependent means the wave function time dependent Schrodinger wave equation will be applied here, and in case of time independent perturbation we will talk about time independent perturbation method, time independent Schrodinger wave equation, which we have applied till now. Till now what we have done, we did not do anything about the time dependent perturbation or time dependent Schrodinger wave equation. We did not apply it. We always used a wave function psi which was proportional to x only, which is only one variable. In case of this time dependent perturbation, psi will have both the variable x and t. Okay, so this will be dealt separately and this will be dealt separately. Okay, this we will see whether we get time to do it or not. But time independent perturbation we will be doing. Means there is no role for time. So we will use again time independent Schrodinger wave equation solutions of different systems, which we have done. Okay. Now this time independent perturbation theory also can be grouped into two categories. So I have written here the Hamiltonian of such system is dependent on time. Okay, and this H prime is actually perturbation. Wherever I have written H prime in this module is actually perturbation or disturbance, whatever you want to say. Perturbation. Prime symbol indicates perturbation. Okay. So the disturbance which you are creating is actually dependent on time, and this we say V naught cos omega t. When a molecule interacts with electromagnetic radiation, okay, then we use this equation, and that gives you the transition probability in between the energy levels. This transition probability is important in all spectroscopy from which you derive selection rules. So time independent perturbation is used to give you transition probability. This we will see whether we can do it or not. But in time independent perturbation also is divided into categories. One is called non-degenerate and another is called degenerate perturbation. So first is non-degenerate perturbation means okay, this is one symbol, and then if I write H naught, this naught is responsible for unperturbed system. Unperturbed Hamiltonian means those systems for which the solution is known. And non-degenerate means if you operate with this Hamiltonian on psi 1, you get energy E1. If you operate with this Hamiltonian on psi 2, then also you get E2 and psi 2. If you operate with psi 3, then you get E3 psi 3. In every case, E1 is not equal to E2, is not equal to E3. So it's a non-degenerate system. Energies are not equal. So dealing with such systems has one theory, dealing with other system, degenerate system, has another theory. Okay, we cannot do the same thing in both the cases. So if for an unperturbed system Hamiltonian, if you go, then what does it mean? It have degenerate eigenvalues, and degenerate eigenvalues means if you operate with the Hamiltonian on psi 1, psi 2 and psi 3, in every case you get the same energy E1, E1 and E1. So all the energy levels are degenerate. For such systems, for degenerate system, there is one theory. For non-degenerate system, there is another theory. For time independent, there is another theory. Okay. So all these three could be will be dealt separately, but we will concentrate more on non-degenerate time independent perturbation. So this forms the basis of the perturbation theory of this course. Okay. So now if you try, so what do we will be doing? We will be doing non-degenerate perturbation method and time independent also. I would say time independent. Time independent perturbation method. Okay. And this method, when I use, this method is suitable for systems which differ in a very small way from one for which the exact solution is possible. This I said you, and everything is written neatly also. System with exact solution is called unperturbed system. System which differs in a small way from the unperturbed system is called perturbed system. I said you. Then the Hamiltonian for the perturbed system is a combination of two terms. This is important. This is the basis. That now, if you have to write the Hamiltonian for a perturbed system, then it will always have two terms, one for the unperturbed system and another for the disturbance. Okay, and this disturbance I said you is given a lambda h prime, where this lambda will be the perturbation parameter. Okay, the eigenvalue and the eigenfunction of the unperturbed Hamiltonian is known. So obviously it is not disturbed, it is original, so the solution is known to you. And we write this h without any superscript, no naught, no pi. This is the Hamiltonian for a perturbed system. Okay, but if you have naught, then it is unperturbed system. If you have prime, then it is the perturbation or disturbance by which the system has been disturbed. Okay, so this is called the Hamiltonian for the perturbed system. I better to write here h without any superscript. Okay, is a combination of two terms. So this is the Hamiltonian for a perturbed system, and this is Hamiltonian for an unperturbed system, and this is perturbation amount. Okay, so what you say, and one thing very important is that this disturbance should be very small, then only the theory is applicable, otherwise it will not be applicable. So what does it mean? If disturbance is small, then the h naught value should be very small than lambda h prime. Okay, if it is not feasible, then we cannot apply perturbation equations or perturbation theorem to the cases. Okay, so till now what we did, any system for which the solution is known is disturbed by a small amount, that can be dealt with in the perturbation theory. But there are three different ways of doing this. For different system, we use different methods. One is for non-degenerate method, another is for degenerate method, and both these are time independent perturbation. And the third one is time dependent perturbation, which tells you about the transition probability in the spectroscopy, or selection rule is derived from this one. This is very important one. Okay, so for non-degenerate time independent perturbation, the only one equation which I have written is h is equal to h naught minus plus lambda h prime. Okay, and so these are the symbols which we use. Psi n naught is the wave function for unperturbed system, E n naught is the eigenvalue for unperturbed system, and h naught is the Hamiltonian for unperturbed system. Unperturbed means system means exact solution of Schrodinger wave equation is known. And so obviously your original Schrodinger wave equation h psi is equal to E psi will operate here. H naught psi n naught is equal to E n naught psi n naught. So this will be applicable. Okay. Then for the perturbed system, we remove the naught value. Psi n wave function for the perturbed system, E n eigenvalue of the perturbed system, h Hamiltonian for the perturbed system. Then the eigenvalue equation to be solved is h psi n E n psi n. This we don't know. This is known, but this is not known. Where h is equal to h naught lambda h prime. Okay. Obviously, I said you earlier that this is known. And the condition is that psi n should be different from psi n naught by a very small amount delta psi. This is a small change. En should differ from En naught by a very small amount, that is delta E is equal to a small change. Okay. So these conditions always remember that it should be a small change. Then only it's called perturbation method. Okay. So you have to solve the solution of this equation is to be known, which will give you En value, energy of the perturbed system, and this you can replace by H naught lambda H prime. And if you replace this one, you have to solve this one, and if you replace H prime by this equation from equation number 2, what you get? This is your now H prime. This was H prime for the perturbed system. So this is unperturbed system plus perturbation into psi n is equal to this one. Okay. So if the perturbation of the system results in changing eigenfunctions of the unperturbed system, psi n naught to psi n and eigenvalue E n naught to E n. Okay. So simultaneously you write this equation also, because psi n naught gives E n naught into psi n naught. This is an unperturbed system. And now you see this is for the perturbed system. So psi n naught changes to psi n, E n naught changes to E n. Okay. So because it's all because of this term, which is perturbation. This is called perturbation or disturbance. Okay. So if now what you do for solving this equation, that we expand this psi and E in a power series in terms of lambda, and if you expand this, you can write psi n is equal to psi n naught, then lambda psi n1, lambda 2 psi n2, lambda 3 psi n3, lambda 4 psi n4. Okay. So similarly, En could be written as En is equal to En naught plus lambda En1 plus lambda 2 En2, lambda square En2, En square, lambda 3, lambda cube En cube plus lambda 4 En4, and so on. Okay. So this when you expand this in a power series, then you can put these values, and when you are expanding it, all these wave functions which I have written, psi n1, psi n2, psi n3 are orthogonal to each other, while this psi n naught we have used is a normalized function, means orthonormal function. Psi n naught is an orthonormal function, and this psi n1, psi n2, psi n3 are orthogonal to each other. So because this property will be used, if you use these equation number 4 and 5 in equation 3, what do you get? Equation 3 was this one, the first equation. Then in place of psi n1, I have written psi n naught, lambda psi n1, lambda 2 psi n2. Rest of the term I have omitted because it's not needed, and the equation will also be a small. Okay. And then En becomes equal to En naught, lambda En1 plus lambda 2 En2, and so on. Then again psi n you have, so psi n again, psi n naught, lambda psi n1, lambda 2 psi n2, and so on. So what will you do? You will multiply. On the LHS you have two terms, on the RHS you have two terms. So you will multiply H naught with this term, and you will write the equation like this one. You see, multiplying this with this one will give you the first term, H naught psi n naught, and this is known to you, is equal to En naught psi n naught, remember. Okay. Then what you do? You multiply H naught with this one. So you have with the second term on the LHS, with this term is the second term. I am giving you a number. Okay. So it becomes lambda H naught psi n1. Then again third term, so lambda square H naught psi n square. So this multiplication is complete with the first term. Then go for the second term. For the second term, you have lambda H prime multiplied by psi n naught, lambda square H prime psi n1, and then lambda H prime, lambda cube. You have lambda square, this lambda, and psi n1. So this lambda will be psi square. Then this lambda H prime and lambda will be lambda cube. This will not be lambda here. It will be lambda cube only. Okay. This will not be there because this is a square of this multiplied by this will give you lambda cube only. So this lambda gone, H prime sin square. Okay. So you remove remove this one. Now it's fine. Okay. So this is your LHS. On the right hand side, if you write, then En naught psi n naught, right hand side, this is your is equal to. So on the right hand side I am writing En naught psi n naught, this and this. Then lambda En naught psi n1, lambda En naught psi n1, then lambda square En naught psi n2. Okay. So this is complete with the first term. The second term, lambda En1 psi n naught, lambda square En1 psi n1, then lambda cube En1 psi n2. So with the second term is also complete. The third term also you have lambda square En square. So you multiply with this also, and if you multiply with third time, then you say lambda square lambda square En square En2 psi n naught plus lambda cube, this lambda and this lambda will be lambda cube En2 psi n1, then lambda 4 En2 psi n2, and so on. Okay. This we can write. Now we say that we segregate then the coefficients of various powers of lambda is equated. Okay. And if you equate the coefficients of various powers of the lambda, what do you find? For lambda naught, this is the equation. See, for lambda raised to the power 0, you have this term and this term in the red only. No other term has lambda raised to the power 0. Here you have lambda raised to the power 1, lambda square, lambda 1, lambda square, lambda cube. Then again here also lambda square, lambda square, lambda cube, lambda square. Everywhere you see there is no other term where lambda raised to the power 0 is there. Means lambda is not present. It is only these two terms where lambda is not present. So H naught psi n naught is equal to En naught psi naught. And what is this? This is the equation for an unperturbed system for which the solution is known, because naught symbol is there. I said, wherever the naught symbol, it is an unperturbed system. So it means there is no perturbation at all, and you need not to worry about this system. For this system, the solution is already known, and we say this to be a zeroth order perturbation, no perturbation, zeroth order perturbation. If you go for lambda raised to the power 1 coefficients, then all in blue will come here, and lambda, you see lambda, 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 and lambda. Rest all is lambda square or lambda cube. Okay. So for this is called, here you have perturbation. This perturbation terms is here. Okay. En1 you have here. So you do not have this and this only. These two account for the unperturbed system. But since the perturbation is there, so you have this also and you have this also. This is called first order perturbation. First order perturbation. And this En1 is called the first order correction to the energy. Okay. This En1 is very important. This we will determine first order correction to the energy of a perturbed system. Okay. And you see here you have psi n1, which is first order correction to the wave function. So that is the goal, finding out the eigenvalue and the eigenfunction. So the goal is to find out the En1, and the goal is to find out the psi n1. So first order correction to energy and first order correction to wave functions we have to find out. So if you count the coefficients of lambda raised to the power 1, it is first order perturbation. If you count the lambda raised to the power 2, then it is a second order perturbation, and you see here what you get. If you compare both these, now you see here, you get this one, En2. En2 is the second order correction to the energy. Okay. And you have psi n2. This is the second order correction to the wave functions. So this we say the second order perturbation. So zeroth order perturbation, no perturbation, original system for which the solution is known. First order perturbation is En1 and psi n1, finding out the En1 and psi n1. Second order perturbation is En2 and psi n2, finding out the value of En2 and psi n2. So these are the goals which you have to achieve while doing the time independent perturbation methods. Okay. And again I said you this is for time independent perturbation. This is applicable for time independent perturbation, and because we have not talked about the time here, and we are going to we are talking now is a system which is non-degenerate. For non-degenerate system we are talking about, and why not third order, fourth order? Normally in chemistry the second order correction is sufficient and it gives you fairly close value, so we don't go for higher order corrections. First order correction, second order correction is sufficient to give you energy, eigenvalue and the wave functions of the perturbed system. Okay, so we will continue talking about this in the next module also, because in the next module I will start with talking about non-degenerate perturbation, first order perturbation, first order correction to energy and first order correction to eigenfunction, the eigenvalue and eigenfunction correction we will talk about first order perturbation. Okay, thank you.